more to try for tomorrow. So the whole idea is that by this point in the course, you're able to write and balance chemical equations. You're able to like figure out what states they're in, write total and net ionic equations, like that kind of stuff. I mean, we've been writing chemical formulas and chemical equations for months now. So none of that stuff ought to be like any kind of new. Let me see what else is in for the week. Schedule for the week. Yeah. Anyway, well, we're in school, except we only have a short day. It's like if we would have just been remote today, we could have had a full period, but we got 2 hour delay, so it's like 26 minutes. Anyway, we'll do the review for the test tomorrow, and then the reactions unit test will be Thursday. If we're in school, you can do it right in class. If we're not, then you just do it at home remote. And then Friday, we have this intro to stoichiometry activity. Okay, so let's see. I got to switch to a different Dilio from Hujum. What's it? All right, so the first problems. Is this combustion reaction. Combustion reactions are always the same, where there's something reacts with oxygen to make usually CO2 and H2O. So this is propene. It reacts with oxygen. And then the products of combustion are CO2 and H2O. And you ought to throw states on there. It says propene gas. Propene is a gas, so you put G for gas. Oxygen is a gas, and oxygen is diatomic, so it's got to be O2. And the products of combustion include CO2, usually, and H2O. And this water is water vapor. So the combustions of combustion reaction are carbon dioxide and water vapor. If you have the combustion reaction take place in a low oxygen environment, then instead of carbon dioxide produced, you get carbon monoxide, and that's dangerous and deadly and poisonous. You might see like on the news, they're talking about like safety. Whenever your power goes out, people might have a generator to run, to be able to have backup power. You never, ever, ever run a generator inside a garage, inside a shed, inside an enclosed space, because the generator needs oxygen to run. And if the oxygen supply goes down, then the generator starts producing carbon monoxide, which is odorless, colorless, just puts you to sleep and then kills you. So you got to keep generators outdoors in properly ventilated areas. They don't run on propene, but they could. So that's how the reaction goes, and then you got to balance it. When you try to balance this, if you start with the carbon, there's 3 carbons here. You might want to put a 3 in front of that carbon dioxide. And then the hydrogens, there's 6 hydrogens, so you might want to put a 3 in front of that hydrogen. But now you run into a problem, because on the left there's 2 oxygens. That's an even number of oxygens. But on the right, there's 6 oxygens in the CO2 and another 3 with the H2O. So that's 9 oxygens on the right, but 2 on the left. And you can't put a 4.5 here. So it turns out that you got to have to fix the problem of having odd numbers of things, you can double everything you've already balanced. So if I put a 2 in front of the propene instead, and then instead of a 3 here and here, you could put 6s, that forces the number of oxygens to be even. Now there's 18 oxygens on the right, like 6 times 2 is 12, another 6 is 18. So then a 9, that'll balance that equation. All right, hydrogen chloride solution. Hydrogen chloride is a gas. When it's in solution, it makes hydrochloric acid. So hydrogen chloride solution is actually hydrochloric acid, HCl, it's aqueous, reacts with sodium hydroxide, sodium, and then the hydroxide anion. I got an ion chart here somewhere. Hydroxide is right here. Hydroxide is OH minus. So NaOH. Sodium has a charge of 1. Hydroxide has a charge of 1. And if you want to know if that's soluble or not, it says that it's aqueous, but you can also check on a solubility chart. Sodium is a group 1 element, and all group 1 elements are always soluble no matter what. So sodium hydroxide is actually like right here because sodium's in group 1 on the periodic table. So NaOH to make water, which is H2O, and that's a liquid typically, and aqueous sodium chloride, NaCl, AQ. And that equation is balanced. There's nothing you have to do. Just one of everything is good. Any questions? It's hot stuff. All right, balance them and figure out the types. All right, well, this one goes, if you start with the lead, there's only one lead on the left, but it looks like we got 3 leads on the right, so maybe you got to throw a 3 in there. And then here we got 3 hydrogens on the left, but 2 hydrogens on the right. So the least common multiple of 3 and 2 is 6. So we put a 2 here and a 3 there. And that looks like better. And then you got these phosphates, and they're all fixed because there's 2 PO4s and there's 2 PO4s. So that's it. And here, the lead replaces hydrogen. And the hydrogen goes by itself, and the lead goes with the phosphate. That's a single replacement reaction. You can also tell it's single replacement because it's an element and a compound make an element and a compound. Then this one's a little peculiar. NH3 on the left, but there's NH4 on the right. So the first thing you can notice is just do it by element. There's 1 nitrogen on the left, but now there's 2 nitrogens on the right. So you know there's got to be a 2 in front of the NH3. And then when you check everything else, 2 times 3 gets you 6 hydrogens. And there's 2 more hydrogens here, so that's 8 hydrogens on the left. And 2 times 4 is 8 hydrogens on the right. There's 1 sulfur on the left, 1 sulfur on the right. 4 oxygens on the left, 4 oxygens on the right. That's it. And here you've got 2 compounds forming 1 compound. So that's a synthesis reaction. It's just 1, or it's 2 things combining to make 1. All right, here we want to predict some products. Maybe the reaction happens, maybe it doesn't. For single replacement reactions or single displacement reactions, you know you got to check the activity series. Zinc might replace silver if zinc is above silver. When you check the activity series, and it's good to have the activity series, a solubility chart, and an ion chart, and a periodic table handy all the time. Zinc is up here, and silver is down there. So zinc is above silver. And because zinc is above silver, the replacement happens. Zinc replaces silver. Now, it turns out zinc usually has a charge of 2+, and that's not on the ion chart. So I won't give you something that you don't know easily what that thing is. But silver has a charge of 1+, and nitrate has a charge of 1-. So if the zinc goes with the nitrate, it's going to have to be ZnNO3 2, and then the silver goes by itself. And that's not balanced. You got to put a 2 in front of the silver nitrate and a 2 in front of the silver, and then that balances the equation. And you can include states too. Zinc is solid, silver nitrate is aqueous, zinc nitrate is aqueous, and the silvers, they're solid. All right, this single displacement. If magnesium is above hydrogen, then the reaction happens. So when you look on the ion chart, well, it's a reaction of an acid, which usually always works anyway. But hydrogen's down here, magnesium's up there. So the criteria is if magnesium is above hydrogen, then the reaction takes place. And here, magnesium is above hydrogen. So the magnesium will replace the hydrogen. Magnesium has a charge of 2+. Hydrogen has a charge of 1+. Chlorine has a charge of 1-. So it's going to be magnesium goes with chloride. That's going to be MgCl2. And then the hydrogens go all by themselves, but hydrogen, you know, is diatomic, so that's H2. So you're going to need a 2 in front of the HCl. And that's balanced. In case you care about the states, hydrogen is a gas. Magnesium chloride is soluble, so that's aqueous. Magnesium is a solid, and HCl, that's aqueous. Aqueous or aqueous. Some people say aqueous, some people say aqueous. Whatever. All right, do these reactions occur? All you got to do is look to see, is the element by itself above the metal in the activity series? I don't know. So tin and sodium, you got to find tin and find sodium. So tin is down here and sodium's up there. So the reaction will take place if sodium is above tin. If sodium, the element by itself, is above, when sodium is the element by itself, it'll replace tin. And here it's the opposite. The tin is below sodium, so there's no reaction takes place. The reaction would happen if the sodium was by itself in the tin. In other words, if it's Na plus SnCl, tin is, well, tin is like 4 usually, but that's not really a thing. This reaction would take place because sodium is above tin. Anyway, zinc and copper. You look for zinc and copper. So zinc is right here, and then copper is down there. So zinc is above copper. The element that's by itself, zinc, is above copper. So there's a reaction. Yes, this reaction does occur. The other two, same deal. Copper is not above zinc, and silver is not above magnesium on the activity series. Those are both no reactions. When does no reaction apply for double displacement reactions? Well, in order for there to be a reaction to take place in a double displacement reaction, you got to have one of the products has to be a solid on the solubility chart. So no reaction occurs, like you can just say that like when both products are aqueous, because then whenever you write, when you write the double or the total ionic equation or the net ionic equation, everything disappears for the net ionic equation. No reaction occurs. There's no precipitate. We actually have an abbreviation for precipitate. It's PPT or just PT. But that's also confusing because PPT also stands for parts per thousand, which is another thing in science. So sometimes people write like PT for precipitate. What can you do to speed up a reaction? So that's the thing about the Alka-Seltzer lab. You can heat it, you can stir, you can like crush the any kind of solid. You can increase the concentration. And then, oh, you can use a catalyst. Catalyst. You can use a catalyst. Any of those kind of things will help you out. If you want to make reactions go real fast, crush the stuff up to a fine powder, have it in high concentration, throw it together, stir it up real fast. Reaction takes place real quick. You want it to go real slow, big chunky things, cold water, don't move it around, no catalyst. It's sort of common sense, but. All right, then we got 3 total ionic equations. Let's see. You figure out the states for each of these things. Are they soluble or not? When you look on the solubility chart, that'll help you determine if they're soluble. So one thing to know is that on the solubilities chart, everything on the top row here, group 1 and ammonium, they're always all aqueous. So anything that's in group 1 on the periodic table, that's hydrogen down through francium, all the way to the left-hand side of the periodic table. Those things are always soluble. Lithium is a group 1 element, so that's aqueous. This is aqueous. Silver nitrate and silver chloride, you got to see if either of those are soluble in water. The assumption is that silver nitrate is aqueous and silver chloride is the solid. That's a precipitate that forms as a result of the reaction. So look at silver nitrate and silver chloride. Silver chloride says solid. Silver nitrate, it says aqueous. So the silver chloride is a solid that forms. This is a solid. This thing's aqueous. The total ionic equation is the list of all the ions that are present in the reaction. So you got a lithium with a charge of 1. Oops, 1 plus. You got a chloride, the charge of 1 minus. There's a silver, has a charge of 1 plus. And you have a nitrate. The NO3 is all one thing. So those are the 4 ions in solution where you're going to make the reaction take place. And the products include silver chloride, and the lithium nitrate is aqueous, so that's a lithium and a nitrate. So that's the total ionic equation. Anything that's aqueous, you write the individual ions separately. And the equation was already balanced. You only need one of everything because they all have a charge of 1. The net ionic equation is the equation that shows only the ions that react to form a solid. So any spectator ions, they're not written in the net ionic equation. The spectator ions include lithium, because the lithium on the left and the right look the same. The nitrates on the left and the right look the same. So the only thing that is different, and it doesn't matter the order, but usually we prefer to write the positive things first. But it really doesn't matter. You can write silver or chlorine then silver. It doesn't make any difference. It really doesn't matter. It's just, it just looks better. I don't know. It's like if you're in algebra class, writing 4x looks right. Writing x4, it's the same thing, but it's like weird. You know what I mean? You don't write x4, you write 4x. Same thing here. We just kind of feel better about positive charges and the negative charges, because also when you write the compound, it's always positive and negative. So it kind of makes sense to be like Ag plus Cl makes AgCl instead of Cl plus Ag. Time flies when you're having fun. We got 6 minutes. Okay.
The calcium and sulfur on the chart, it had a D.
Yep.
So what is that?
Yeah. I won't put one of those like on the test. I'll tell you what it means. So anyway, when you write these out, these are all aqueous, and on the chart it says D, means dissociates or doesn't form. We still got there's still like 5 minutes left, I think. Yeah, right? 10:38? 10:38, yeah. Anyway, when you write these out, so I'll write them out. We got 2 sodiums with a charge of 1 plus a sulfur, and that's a charge of 2 minus. And then you get a calcium, and a chloride. There's 2 chlorides, 2 Cl, 1 minus. I didn't mean to put an arrow there. Plus 2 chlorines, 1 minus. Makes 2 sodium chlorides, so that's going to be 2 sodiums and 2 chlorines. So if it says anything except AQ, you leave it like it is. I'll tell you what actually happens. This is sort of a bad example. It turns out that calcium sulfide is neither a solid nor is aqueous. Instead, calcium sulfide reacts with water, and you get calcium hydroxide and hydrogen sulfide. The calcium sulfide reacts with water molecules to make calcium hydroxide solution and sulfur hydroxide, which is H2S. Sulfur hydroxide, that's the next part of the reaction. Sulfur hydroxide, that's the smell of rotting eggs and like sewage gas, like just disgusting, like dookie. Anyway, here in this reaction, so the idea is that the sodiums are the same on both sides and the chlorines are the same on both sides. But what is different is that there is the sulfur and the calcium. And you could write those in opposite order. Makes calcium sulfide, CaS. And it has a D, which means it dissolves, or which means it dissociates. In other words, that's not the final product. It's neither ionic in solution nor is it a solid, but calcium. So what happens is calcium sulfide and the water react to form H2S, H2S plus Na or calcium hydroxide, CaOH2. Anyway, the last one, let's see. Well, it's not the last one, but this is aqueous. This is aqueous. This is a solid, and this is aqueous. I don't know. You should end up with a net ionic equation of cobalt, which is aqueous, and the carbonate to make cobalt carbonate. This is a hypothetical. Oh, wait, no, this is 12. Sorry about that. I'm not even. There's a number 13. I was writing like, that's for number 13. This is a zinc and a chlorine, 2 chlorides, make zinc chloride, make a, oh, it's a hydroxide, 2 OH minuses, make zinc hydroxide. I was thinking of the number 13. Like I have a solution written down for number 13. That wasn't like the end one. Anyway, I'll write and talk more about like 12 and 13 and put videos online for those two. But best thing to do is that there's the other one that's a single page. They're just some more practice. If you can do those and do them quick and they all make sense, that's great. We'll go over those tomorrow and I'll answer questions about that. We go over the 12 and 13 tomorrow, and then the other review, and then Thursday the test will be posted for doing kind of like all the chemistry.
Yeah. Will we have the solubility chart for our test?
Yeah, like I mean, do you have a copy of it printed out?
Mm-hmm.
You know, yeah. Like you don't have to memorize stuff. You know,
Yeah,
memorize solubility charts, activity series.
Well, at this point, I feel like a lot of them I just remember, but
yeah, over time you do get used to it, but you know, you can use them as references, right?
Yeah, I just figured it'd be nice to have it to check.
Yep. More stop recording.